Does anyone in this room know who Tom Paseka is? Has anyone met Tom Paseka? Tom Paseka works at Cloudflare, which is the company that I work for. And he is the reason that I'm here today. I normally don't talk to audiences like this. I normally don't talk to people who work in networking. I normally talk to developers, engineers of applications. Usually if serverless applications, a lot of the time they'll write a language like JavaScript, and they don't have the problems that you have. They don't think in the context of microseconds and millions of users and the incredible level of multi-tenancy that you have to deal with in a lot of these systems. And so normally I would not be at an event like this, unfortunately. But Tom, who works on our network infrastructure team, asked me to apply. And the reason he asked me to apply is because he thought that the things that we had learned from having to build a really highly multi-tenant system that could allow all of these developers to deploy code onto our network could be valuable for this audience, and that there was some value in taking the experiences learned in a very different world and trying to bring them in to the conversations that we're having here. And obviously the conference was gracious enough to give me the time to speak with you today, and all of you were nice enough to show up, which I deeply appreciate. I'm going to try to convince you of two things in the context of this talk. The first is that there are alternative ways of thinking about virtualization, thinking about the problem of letting someone run untrusted code in an environment that they understand on a machine. And that some of these different methods of doing virtualization could work better in an edge computing environment than trying to map the things that we've been doing for the last 40 or 50 years into that world. And I may or may not succeed at convincing you of that. Hopefully, at least it's interesting. The second thing that I will try to convince you of, based on our experience working in this edge computing world for the last few years, is that the applications of edge computing are a little different than what people commonly think about. Classically, people have talked about things like self-driving cars or facial recognition from security cameras or IoT as the place where VR and AR is one that we heard about this morning, as the place where edge computing is really going to shine and be relevant and be valuable. But what we have seen is that if you can change the economics of it a little bit, it actually makes a lot of sense for people to deploy almost all code to the edge. If you have the capability to run your application code close to your users, there isn't an advantage generally in not doing it. So if you can change the cost model, which is what the first part of this talk is going to cover, then all of a sudden the market for edge computing goes from being a bunch of people with really specific esoteric applications that require the world to move forward in order for them to be relevant to virtually every developer on Earth, essentially everyone who's sitting down and using AWS today. So those are obviously two things that are not guaranteed to be true in practice. Maybe we have a 10% chance or a 30% chance or a 50% chance. But we at least find it very interesting. We've had a lot of success in the last couple years working on those systems. Before I talk about kind of what we do and what we built, I want to take a step backwards, partially because I just really think the history of technology is interesting. The way that we build things to try to solve problems and change the way people do their work is a very interesting thing. And partially because I think it's really valuable to put what we're doing now in context. This is the Leo 3. One side of this is the Leo 3. The other side of this is the company that made it. It was the first system that did time sharing in 1961. Before 1961, you would buy a computer and it would run one program at a time. So you would go to IBM and buy a machine that was going to tabulate the census, and then you would give it a bunch of data and it would tabulate the census. But the Leo 3, even in 1961, even though it was built with Mercury delay line memory, had multitasking. You could give it multiple programs and it could run them simultaneously. And this T company built it because they needed a system that could tabulate their accounting. And they weren't able to buy a system that they liked, and so they decided to build it in-house, which is something that you still occasionally will see a company do today. So they built a couple versions, and by the Leo 3, it had a version of time sharing. And all of a sudden, it's possible to run multiple programs at the same time. Multics, and this is a G645, it's a room-sized computer that would run the Multics operating system, was built in 1965. And Multics allowed for a bunch of things that we do today. It had a hierarchical file system for the first time, so slashes to separate directories from files. It had ring-based permissions, so processes could run with different levels of permissions. And it built a lot of the security tools that you need in order to really let multiple people who maybe don't trust each other all run code on the same machines. And then Unix came along. A couple developers who worked on Multics but thought that it was too complicated sat down and on their PDP-11 wrote a new operating system that everyone could use, but integrated a lot of those same concepts. And it really built out this permissions model to the point where you could have a whole bunch of people all sharing the same machine simultaneously and not destroy each other's work. It became very popular, was adopted in a lot of areas, but was also somewhat expensive until Linux. 1991, Linus Torvalds builds his own version of Unix that implements a lot of the same APIs, but is totally open source and everyone can use. And all of a sudden, it becomes incredibly popular. And you end up with these rooms full of servers that are all running different variants and versions of Linux in different ways. Then virtualization is invented. And all of a sudden, I can run multiple copies of Linux on the same machine. And a very enterprising bookstore in Seattle figures out that they can sell people this ability to run Linux on a server by the hour. And all of a sudden, I can have as many servers as I want in US East 1, or I can have them in US West 2. I can put servers in a location on Earth. And that's where we found ourselves in 2016, when we would get on calls with customers running a very large network, and they would ask for the ability to run code on our network. They asked for the ability to, for example, we talked to a vendor of A/B testing for websites, and they said, right now we slow down all of our customers by up to 500 milliseconds. And if you could just let us run our code on your network, essentially on our edge, we have 194 points of presence around the world, which is not as big as many of your edges, but it's pretty big by application development standards. We would be able to dramatically speed up the ability to develop these applications. And we can't just deploy to US East 1 or US West 2 because they only have 20 points of presence. They don't have the density. They aren't close enough to customers. We need edge computing. And we told them, no. It doesn't make sense for us to let you do this. Because if we're going to use our existing systems, we either have to write the code ourselves, or we have to figure out some way to let you run untrusted code on our machines. And there's no good way to do it. If you use traditional containerization or virtualization, it's going to slow down your ability to develop this code, and it's going to slow down the ability to execute the code. And here's one reason why. When these original multitasking machines were invented, they came up with this idea that they could very quickly switch from one person's code to another, and in the process, pretend like they were executing multiple people's code at the same time. It's called a context switch. The problem is a context switch takes some time. You have to swap a bunch of memory in and swap it back out. And that works totally fine when you have one program or 10 programs or 100 programs running on a machine. But we have 20 million websites that use our network. And so if 1/10 or 1/100th of them all wanted to run their code on one of these machines, we would end up spending all of our time context switching from processing one person's request to processing another. So the fundamental architecture of how a processor switches between pieces of code to write just doesn't map to an environment where you're getting hundreds of thousands or millions of requests per second that are all destined for different people's code. So that's the first problem. Another problem is the standards that were developed in order to write code onto these mainframe type systems don't necessarily adapt that well to this world. If you analyze it, you end up realizing that you spend a tremendous amount of time handling interrupts, doing context switches into those interrupts, and dealing with the security barriers that have to be created to let you run code in a shared environment. When you get the keys to the castle in Linux, when your code is ready to run, you basically get to take over the entire processor core. And that means you have a tremendous amount of power. And so to protect the operating system, to protect the other people, there has to be a tremendous amount of code that runs in the operating system to create all of the security barriers necessary in order to successfully allow you to execute code without being able to tamper with anything else. And obviously, in the modern world with Spectre and Meltdown, even those barriers have fallen apart. But fundamentally, it eats up a ton of time. And then another big problem is it takes a lot of time to start up code initially. If you want to start a Node Lambda, which is a serverless programming platform that Amazon has, it takes at least half a second to start up a new piece of code. And if you want to start it up in response to requests coming in, some percentage of those requests are going to be delayed by at least half a second, which is really, really unpalatable for someone who came to this whole world in order to get better performance. It makes perfect sense that Node would take half a second to start up because it was designed to be deployed once a week. No one ever thought that it would be really, really important for the virtual machine to be able to start quickly. But it suddenly is in an environment where you need to be able to start and stop these different people's code really quickly in order to use memory effectively. So again, going from a world with a mainframe where you might run 10 node processes to a world where a server might run 10,000 or 100,000 all in a shared environment, the economics suddenly fall apart. And so we have this vision of the future that's built on top of these tools that were created for a very, very different environment, for an environment that actually existed long before the internet did. And so the question that we had is, can we come up with an alternative way of doing some form of virtualization, of letting these customers sit down and write code that could run on our hardware, but be able to run 10,000 different people's code on a machine, be able to start it really, really quickly, affordably. And so here's kind of a codification of those goals. We need to be able to run code on distributed machines in an isolated way. We need the code to not consume too much memory, because that node Lambda is 35 megabytes of memory, even if it's not running any code. And if every one of our customers takes 35 megabytes of memory across the thousands of machines that could potentially get requests for them, it would be unbelievably expensive. We wouldn't be able to sell it to everyone on the street. We could only sell it to the largest customers on Earth. We need to spend as much of the CPU time not context switching, but actually executing people's code as possible, because these economics are really, really tight, and it's very important that we get all of the power out of a CPU core that we can. And people shouldn't, and this last is kind of more of a want, but people shouldn't have to think about regions, this concept of availability zones and regions. They should just be able to deploy code and have it run in the way the internet runs, deployed everywhere. And we kind of found a product that solved a lot of these problems. It's the Google Chrome browser, as surprising as it might be. It turns out that this is a tool that runs untrusted code. It has minimal memory overhead. It has to, because you'll get very upset if one of your tabs suddenly starts using a bunch of memory. And it has to start running new code very, very quickly, because that's what happens when I go to google.com. It has to run all of these different pieces of code as quickly as possible. So it turns out, as bizarre as it may sound, they have solved, with the V8 JavaScript and WebAssembly engine, a huge swath of the problems that we had. They just solved it to run in the browser instead of on the server. The brilliant element behind all of this is, inside a single process, I can now have one virtual machine and have it run 1,000 different people's code, or 10,000 different people's code, or 100,000 different people's code cooperatively. So instead of having to have a containerized process for everyone's code that might have a virtual machine in it, the JVM or node, and might have a little piece for their actual code, I can run one virtual machine and I can start each person's code independently and have security barriers between them, all running in a single process. So there's no context switches. The operating system's always running the same process. But I can have these little, we call them isolates, because V8 calls them isolates, that represent each person's code. And I can start them almost instantly with very, very little memory overhead. So I'm essentially moving all of the multitasking that was originally invented by the T company, and then was done by Multics, and then was done by Unix and Linux. And I'm saying, I appreciate all of the work that you did, but it is no longer applicable to the type of virtualization we're doing today. I'm going to give you a single process to run, and I, using this virtual machine, will make decisions about whose code should be running when, and will maintain security barriers around them. Now, if we had to build that ourselves, it would have been incredibly difficult, because writing user space code that can execute arbitrary people's code securely is really, really dangerous. Fortunately, though, this V8 engine that's in Chrome has what I assume to be millions and millions of hours of work put into it to make it secure and to make it performant. And as unintuitive as it might be, it actually is very, very efficient in running code on the server. I know classically we like to think that JavaScript is a very slow language, but it turns out that it is a just-in-time compiler that can compile it down to code that's almost as fast as machine code that you might write. And through WebAssembly, it supports almost every compilable language. So it's not just JavaScript that we're talking about. It's Rust, it's C, C++, this huge swath of languages that's now becoming available for WebAssembly. So we have no VMs and we have no containers, which is really surprising, because I know the party line for a long time has been, in order to build edge computing, we need to use the best-in-class virtualization technology, and that's Kubernetes. But we're no longer using Kubernetes in this model. We're not using containers at all. And we're able to run millions and millions of functions, and we're able to sell 3 times more compute per dollar and have an empty virtualized function use 1/10 the memory and have 100 times lower cold start time. And the 100 times lower cold start time is incredibly important because 5 milliseconds is fast enough that we can do it in response to a request and no one notices. So if a request comes into a machine in Djibouti or Ulaanbaatar, Mongolia, we can start up a function, respond to that request, and if we want to, shut down the function fast enough that the requesting user will never notice in the scope of internet latency. And because we can do that, a lot of the time it's cheaper for us to process a request in Mongolia than it would be for us to pay for the bandwidth for it to get all the way to the United States. So it isn't edge computing, the super expensive esoteric thing that only a few people can use. It's edge computing. We now process that request for less money than it would have cost to bring it all the way to US East 1. Totally different economics. And we have this deployed across our network. This is a slightly old map, but we have 194 points of presence that currently run huge numbers of these functions every single second very successfully. And they do it with no regions, no availability zones. So when a user deploys code, it will just run everywhere in response to a request. And that is possible, again, because these use so little memory. And we can scale them up and down trivially, basically instantly. So we don't have to ask a user to pay us more if they want to get into certain data centers, because we get to decide when we're going to start a function, how many copies of it we're going to run, when we're going to stop it. And we get to only pay a handful of megabytes of memory penalty for each one that we start. So again, the economics, totally different. And from a customer's perspective, they're able to write code and deploy it, and they don't need to think about scaling it at all. It can get millions of requests per second instantly, and we can start all of those instances just in response to requests coming in. This is, I know it's really hard to see, but the red line is a worker, and then the blue line and the green lines are different types of Amazon Lambdas. And this is showing the amount of latency relative to the percentile. So you can kind of see at the 50th percentile, this worker is responding in 20 milliseconds or something. And the Lambda at edge, which is Amazon's edge computing technology, is all the way in the 200s. A part of that is network latency, because we have a slightly denser network than they do. But the majority of it is actually just the ability to not have cold starts anymore, to start these very, very quickly and sell more CPU for the same amount of money. So that's part one of my pitch, sort of super blitz, high energy, what we're trying to do and why we think it's interesting and why it's been valuable for our customers. And so obviously now we live in a world where we are able to go to that customer who wants the ability to deploy code on our edge, and we can sell it to them. And we can sell it to them for pennies per million requests. And we don't have to get a big upfront payment for them to do the deployment. We don't have to get a big payment for them to pay for the amount of memory overhead that we're going to have running their containers. And they don't have to make decisions about how to scale them or worry about the number of requests that they're going to get. It, for lack of a better word, fixes a lot of the problems that we see in other traditionally deployed containerized process architectures. The second thing that I want to talk about, I only have a couple slides for this, is kind of what we see the future looking like. Because, again, a lot of the people who think about edge computing, they think that it's going to be this, that people really are going to have these very different needs than they have right now. And if we build out the infrastructure, those people will just come. They'll knock on the door and they'll say, I really needed to do augmented reality. And thank God you're here. And I hope that happens, because I want to live in a hoverboard future as much as everyone else does. But it's hard to know when it will or if it will. One thing I do know, though, is right now people build applications. And they write code that they need it to run somewhere, and they need it to be able to interact with data. They need to be able to respond to requests. And we've built a lot of hacks to let them do this with traditional architectures. The entire CDN, in fact, is a big hack. It's this idea that if you split up your resources and some things are static and other things are dynamic, we can make the static ones faster for you. But you have to do a bunch of work. But eventually, we can kind of make some of your resources fast. That is a big hack in order to support the fact that we can only put servers in a few locations around the world. And we have all these great new modern distributed databases, but they use incredibly complex consensus protocols in order to allow you, the developer, to pretend like you have a monolithic database, even though it might have a couple nodes in different places around the world. In some ways, that's also a very big hack, trying to allow you to think that you have a monolithic mainframe somewhere, even though, oopsies, my users are actually all around the world. It is possible, though, that the future that people really want is one where they write code and it just runs across the entire internet. And they don't have to think about where their servers are. They don't have to know that they're doing edge computing. They just know that they're deploying software and it's running really close to all their users. And that's where it comes back to this network question, because obviously, everyone would want to be able to run it in cell towers, would want to be able to run it in every node they can on Earth that supports the ability to execute this. And there's no reason that that shouldn't be possible if we can change the economics of deploying code onto the edge. So we do have a platform that people can use right now. It's at workers.cloudflare.com. A lot of people use it to write code and deploy it, mostly in JavaScript and in Rust, and run it on the edge. Obviously, we're trying to build it out in terms of the number of points of presence that we have. We're always trying to build that out in terms of the capabilities that it has. But I'm mostly excited about the architecture, the idea that moving this virtualization to a different point in the stack could change the way that we're all able to allow people to deploy software, could change the way the internet works and the way networks work. Does anyone have any questions? Yeah.
Sorry, maybe I'm a bit slow. So what you're saying is basically as long as you can run, say, the Chrome-based V8 engine, you can basically run, you basically have a virtualization platform for applications? Is that what you're saying?
So when you think about what V8 is, and for people who don't know, that's a great question. And I'll actually repeat the question because, yeah, I'll repeat the question. The question was, how can you actually run this? Like, if you just have V8, does it work? V8 is a JavaScript and WebAssembly engine, and it's designed to take a bunch of isolates, which is a concept that it invented, and cooperatively all run them on top of a processor. And each of these isolates get protection from each other. So they're just like processes on an operating system, but they're kind of a level higher. And so I can write code and you can write code. We each get an isolate. We each have our own memory context, and we each can run code independently. And it all happens in a single process with a single virtual machine that's cooperatively switching between which one it'll run, very similar to how an operating system works. And that's what V8 gives you. If you want to build an actual platform on top of it, you have to build a few things. You have to decide when the isolate should be started and when they should be stopped. You have to build the entire programming environment around it so it can run code, but it doesn't, for example, have a cryptography API. It doesn't have an API for fetching resources from the web. It doesn't have a lot of the primitives that you would generally expect. And we decided to solve that problem by trying to replicate the environment of a web browser as much as possible. So we use like standardized APIs like the Fetch API and the Web Crypto API that have been standardized for use in a web browser, and we just run them on the server instead. We've implemented them ourselves in C++. But you could decide to build any sort of environment you really want to, using V8 or Mozilla's equivalent CraneLift to be the actual execution environment.
Sorry, I have a quick question. Mm-hmm. So is this geared towards largely like stateless kind of services, similar to like Lambda, like you're mentioning, or like how stateful can this go?
That's a good question. So you can have basic forms of state in the idea that you can keep an isolate running for an extended period of time, just like a process. So you can have state in the sense of memory that you access that's on an individual machine. We are building storage technologies on top of this that are trying to work in the same way, where they really understand the concept of the internet and they don't try to keep everything everywhere. But that is a whole nother effort and a whole nother talk on top of this of how you can try to incorporate state, again, in a way that is accepting of the internet's architecture and isn't just trying to make a mainframe work in a distributed way.
Your solution is only, I shouldn't say only, but basically based on JavaScripts. Like you have to write your program in JavaScripts at least. So comparing with Amazon services, yours is a little bit not apple to apple, isn't it? I mean, I can just go down and run a C build on an Amazon, but not in yours.
That's 100% correct. So the one disadvantage, or I wouldn't say the big disadvantage, I'm sure there are more, is you cannot lift and shift. You can't take an existing compiled piece of code that was meant to run on Linux and run it in this environment, because we don't provide the same APIs. We're providing web platform APIs, not traditional operating system APIs. So it is somewhat limiting in terms of people's ability to take existing code and run it. That said, it isn't just JavaScript. WebAssembly is a standard that's kind of been coming out recently in the last few years to let people compile other languages into a form that V8 and CraneLift can run. So you can use C, C++, Rust pretty well, and there are experiments with Go and other languages as well. That might mean you can reuse libraries that you were able to use in a traditional environment, but it's always going to take a little bit of work in order to move something into this world. That has been a huge issue for us because serverless, which is kind of the programming model that we use for all of this, is different enough already that no one's really able to lift and shift a lot of code to begin with. pretty much everyone has to write at least some parts of their code from scratch to work in a serverless world. And so it isn't that hard to get them to adapt to this web platform world at the same time. But yeah, there are definitely people who wish that we could run traditional processes.
Do you see this primarily focusing on, or thinking about like a microservice sort of architecture, right? What a lot of people talk about. And then this kind of an architecture is a little bit different. If I deployed multiple isolates, in terms of how they communicate with each other, is this more of like a CDN use case? Like it would be deployed at the edge, and then a lot of my logic would still live in the cloud sort of thing?
So that's an awesome question, and it's really, really cool. If you write an isolate, and I write an isolate, and let's say I just make an HTTP request to yours, as if we were totally separate services. In this model, they can actually both be ran on the same machine, in the same process, but with isolation barriers between them. So when let's say I make a request to Stripe's API. In a traditional world, that has to go out through the internet, find a server where Stripe's API is running, and be handled, and then the response would come back. But if Stripe and I are both implemented as workers, we're able to take that request, realize that this is actually for a worker, spin it up on the same node, and actually run it in the same process. And so it's as if Stripe's entire API was like a library that you could bring in, but it has security barriers, and they get to deploy it whenever they want. So it's really cool, and I'm very optimistic about it.
Yeah, so it's like so in the context of, let's say that it realized like this is not suitable for me, then it would hand off. So let's say I needed a database at some point, it would hand off that functionality into a database suited sort of processing area. Like this wouldn't run a database necessarily, like within the context of where this is living, or
we're working on it.
Okay.
Yeah, the storage stuff is where a lot of our focus is right now, and so we are doing what we can to build out storage capabilities similar to what you're talking about. Anyone have a last question? No? Thank you very much. I really appreciate your attention.